Good morning, children. Sairam. Children, today we are starting with the last group of the periodic table, that is group 18 elements. Now, group 18 elements, you all know that they are the inert gases. So, inert gases, as they are very less reactive, they are all present in gaseous state, their octet is completely filled, so we don't have to study much about this, and they do not form much compounds also. This is a very small topic for today. Now, the elements that are present in group 18 of the periodic table are helium, neon, argon, krypton, xenon and radon. Now, the atomic number for helium is 2. For neon, it is 10. Argon is 18. Then krypton is 36. Xenon is 54. And radon is actually a radioactive element, have a very short life. So it has the atomic number 86. Now, if we see to the outermost shell electronic configuration of the elements, then for helium it is 1s2. Now, the outermost shell is the first shell and only s orbital is present, which is completely filled. So, helium neither wants to give an electron nor it wants to take an electron. For other elements, the outermost shell configuration is like 2s2, 2p6. Second shell is the outermost shell. It is completely filled. S has 2 electrons and P has 6 electrons. Similarly, for argon also, it is ns2, np6. So, all the elements for argon, the value of N is 3. For krypton, it is 4. For xenon, it is 5. But you all can see that the atom is having completely filled electronic configuration. So, many of the properties, including the gaseous existence in the gaseous state and their interactive nature, are described to the closed shell structures, on the basis of the closed shell structures. Now, next thing we are discussing is the ionization enthalpy. You all know it is the amount of energy required to take out an electron from these atoms. Now, you all know as their electronic configuration is stable, so these gases exhibit very high ionization enthalpy. It is not possible to take out an electron from the atom. Why? Because their octet is completely filled. They do not have a tendency to give the electron. They don't want to give any electron. They are completely filled. But you all know as we move down the group, the size of atom is increasing. When the size of atom is increasing, then the hold of the nucleus on the outermost electron decreases, and as the outermost electron is very far from the nucleus, so it can give outermost electron, those elements which are present down in the series. Though ionization enthalpy is very high, but down the group ionization enthalpy is decreasing. Next is atomic and ionic radii. Atomic radii, if we talk about, it always increases down the group with the increase in atomic number. Size is increasing down the group. Smaller, bigger, quite more bigger and very big. So, atomic size is increasing down the group. Third is the electron gain enthalpy, EGE. Electron gain enthalpy means the amount of energy released when an atom takes up an electron. But since noble gases have a stable electronic configuration, they do not have a tendency to accept any electron. They don't want any electron, so their electron gain enthalpy values are largely positive. That means if we want to add up an electron to the outermost shell of these atoms, we have to supply a lot of energy. Now next thing is the physical properties. Physical properties, you all know all these are present in the gaseous state. First thing is they all are gases. Second thing is they all are monoatomic gases. Monoatomic means only one atom is present in the gas. They do not form a bond because of stable configuration. So they are monoatomic gases. Now they all are colorless, odorless and tasteless. That means they are colorless, odorless and tasteless. Neither they have a color nor an odor nor they have a taste, but they are sparingly soluble in water. They dissolve in water. Next thing is they have very low melting and boiling point. That means the MP and BP, boiling point and melting point, are very low. Why boiling and melting point are very low? Because there is no interaction between the atoms. So as interaction is not there, molecules are already apart, so their boiling and melting point is also very low. Now many a time a question comes in the board exam that which intermolecular interactions exist between the molecules of the nuclear, these inert gases. You have to remember that only one type of interaction exists between these elements, that is weak dispersion force. What it is? Weak dispersion forces. So it is only one type of interaction exists between the molecules of the nuclear, the inert gases, that is the weak dispersion forces. Helium has the lowest boiling point and it is 4.2 Kelvin of all the known substances. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass and plastic. Now a question is there, why are the elements of group 18 known as noble gases? Why they are called noble gases? Because they do not react with any other substance as their outermost shell is completely filled. Another question is there, noble gases have very low boiling point. Why? Because of the existence of only one type of interactive force, that is weak dispersion forces. Therefore, these liquefy at very low temperature and have low boiling point. Now coming to the chemical properties. We are studying the chemical properties now. Children, in chemical properties, we don't have much to study about as these noble gases are very less reactive, or you can say inert, due to the presence of fully filled orbital, and their ionization enthalpy is very high and electron gain enthalpy is also highly positive. But still there are compounds which are formed by the element xenon. Only xenon is capable of forming compounds. And who discovered these compounds? Neil Bartlett. Neil Bartlett was the scientist Neil Bartlett was the scientist who discovered the compound out of xenon. And what made him to go to this conclusion that xenon can form compound? This question also came in the board exam once, that what inspired Neil Bartlett to form compound out of xenon. Children, actually he was studying the compound of platinum, oxygen and fluorine. Now he formulated the compound of platinum, oxygen and fluorine, and then he realized that the first ionization enthalpy of oxygen is around it was around 1175 kilojoule per mole, and which was almost identical to that of xenon. Xenon and oxygen atom have the ionization enthalpy of 1170 kilojoule per mole and 1175 for oxygen. So Neil Bartlett was remembering that the ionization enthalpy of both the elements is quite similar. So he made some efforts to prepare same type of compounds with xenon as he was making with oxygen and platinum and fluorine, and he was successful in preparing another red colored compound by mixing PTF6 with xenon. When he mixed PTF6 with xenon, he was able to isolate the compound XePTF6. So he was successful in making the compound out of xenon. Now after this discovery, a number of xenon compounds were made, and with most electronegative elements like fluorine and oxygen. So different compounds were made later on. Now the compound of krypton are very few. Krypton also makes compound, but there are very few. Only the difluorides like KrF2 have been studied in detail. Compounds of the last element, that is radon, they have not been isolated yet, because the element radon has very short life, and no true compound of helium, neon and argon and krypton are present. They have not yet been developed, neither anybody has learnt about these helium, neon, argon and krypton. We can say krypton has formed a little bit of compounds, but helium, neon and argon has not formed any of the compounds. So we have to study in detail the properties of the compounds of xenon only. Now children, xenon can form compounds with fluorine. Xe and F can form compounds like Xe and F can form compounds like XeF2, XeF4, XeF6. Now these type of compounds, they are the binary compounds of xenon, or you can say the binary fluorides, XeF2, XeF4 and XeF6, and they are formed by the direct reaction of the element under appropriate experimental condition, like high temperature of about 673 Kelvin is required for the formation of XeF2. For XeF4 873 and for XeF6 573 Kelvin temperature is required. Now XeF6 can also be prepared by the interaction of XeF4 with O2 and F2. Now these are the important compounds. Now children, you have to remember that these three compounds are colorless crystalline solids, and they sublime readily at 298 Kelvin. They are strong fluorinating agents. That means they can easily give fluorine to some element and can fluorinate that compound. They are readily hydrolyzed by the traces of water. XeF2 is hydrolyzed to give HF and O2. That means they readily react with water. Now the most important thing related to them is what comes in the board exam is their structure on the basis of Vespers theory. Children, you all are already familiar with the Vespers theory. I request you all to go through the structures. Now, if we talk about XeF2, xenon, the outermost shell configuration is ns2np6. Now, if we draw the orbital diagram in the ground state, then in s orbital 2 electrons are there, and in p orbital 1, 2, 3, 4, 5, 6 are already there. Here xenon has to form 2 bonds, so this electron will go to higher orbital, 2 unpaired electrons will be formed, and these will be the paired orbitals. That means it will have 3 lone pairs and 2 bond pairs, and the hybridization state will be sp3d. Now, when sp3d is the hybridization state, then the geometry is trigonal bipyramidal. Xz will be present in the center. A triangle will be formed between the 3 lone pairs, and 1 bond above the plane, 1 bond below the plane. So, geometry you can simply call it to be linear because 3 are the lone pairs. These are the lone pairs of electrons. So, the geometry of XeF2 molecule is linear. Now, coming to XeF4. XeF4 molecule again will have how many lone pairs? 2 electrons will remain in the s orbital as such, 4 in the f orbital, 1, 2, 3, and this 4th one will be paired, 6 in the orbital, 5, 6. Now, in order to have 4 bonds, it needs to have 4 unpaired electrons. So, this electron shifts, this electron also shift. The hybridization state becomes sp3d2. When hybridization state is sp3d2, sorry, what I have written? It will be sp3d2. For sp3d2, geometry should be octahedral, but it has got 2 lone pairs. So, what will happen? 1, 2, 3, 4. 4 bonds with fluorine will be present in this manner. 1 bond above the plane and the other one lone pair below the plane. These 2 will be the lone pairs, and we will call the geometry to be square planar. For XeF6, XeF6 will be Xe present at the center, 1, 2, 3, 4 xenon present like this, 1 xenon above the plane, 1 below the plane, and 1 will be the lone pair hanging on the upper plane, and this bond will be slightly tilted, it will not be straight, and the geometry is called distorted octahedral, simply called octahedral wedged geometry. So, this was about the xenon and fluorine compounds. Next comes the compounds between xenon and oxygen. Now, xenon and oxygen compounds are also there. Hydrolysis of xenon fluorides gave XeO3. XeO3 compound is formed. Similarly, XeOF4 is also found. Similarly, XeO2F2 is also there. Now, you have to study in detail the chemical reaction for the preparation of these 3 compounds and their geometry. Now, children, as you are already familiar with the Vespers theory, I hope you will be able to draw the geometry of these compounds, and will wind up for today now. And in the next presentation, we will be only discussing the questions related to the chapter P block elements. Thank you and Sai Ram.